In this lesson, you'll get an introduction to the different types of chemical reactions that we'll be working with and how those chemical reactions are shown in balanced equations. So it's important that we review some things like physical and chemical changes. A physical change is a change that occurs in shape or size, color, or state of matter, remembering that state of matter refers to things like solids, liquids, and gases. This is a change without a change in chemical composition. So you looked at this when you completed the mixtures lab earlier this year. So for example, physical changes might include tearing a piece of paper, cutting your hair, or changing from solid to liquid to gas, or in the reverse direction. Physical changes do not indicate chemical reactions. On the other hand, a chemical change is one where a substance becomes another substance that has different properties from its original components. These are changes that usually cause heat, sound, light, odor, a fizzing or foaming, which would be indication of releasing a gas, a color change, or forming a precipitate. So for example, when you mix vinegar and baking soda, if you think back to any time where you've seen this done, you know that you get a lot of like explosive foaming and bubbling, and this indicates that a chemical reaction has occurred and caused a chemical change. If you burn anything, that is also a chemical change because you are changing the properties of the original substances into something new. Even something like spoiling food or soured milk, that indicates a chemical change as well, in that a reaction has occurred where the original substance changes into something new. The only 100% way to know whether a chemical change has occurred is if you do a chemical analysis. You actually analyze the compounds that you start with and then the compounds that you end with to see if they are made of the same elements. So mixing vinegar and baking soda in terms of a chemical equation looks like this. Another thing to consider when we talk about chemical reactions is their rate. The rate at which chemical reactions take place are based on the number and speed of the interaction or the collisions between the different particles. These can be impacted by temperature. A temperature is a measure of the average kinetic energy of the particles in a sample of matter. So if you increase the temperature, the particles are going to move faster. You will get more collisions, and so the rate of chemical reaction would increase. For example, when you increase the temperature when you're cooking something, that causes the reactions that are changing the original compounds from one thing into another. Like for example, baking a cake, that increases those collisions and therefore causes the chemical reaction to happen faster. Another thing that affects chemical reactions are surface areas. Surface area is the amount of material that comes into contact with the reactants. For example, when you cut a potato into smaller pieces, it will cook faster because you're allowing more surface area to come in contact with the higher temperature water. Another thing that affects the rate of a chemical reaction is the concentration, meaning how much of the substance per volume do you have. The greater increase you have in concentration, the faster your chemical reaction will run. So if you turn the valve on a gas stove to increase the concentration of methane molecules, you will have a faster chemical reaction. And finally, catalysts. These are enzymes. Enzymes are organic molecules that help speed up chemical reactions. But the crazy thing about a catalyst is that it is not consumed in the reaction. So for further information about this, take a look at page 97 in your textbook. So a chemical reaction is the process by which a chemical change occurs. In any chemical reaction, the atoms that you start with are then rearranged, chemical bonds are broken in the initial compounds, and then reformed, creating some new substance. For example, we see at the bottom of the screen hydrogen and oxygen. We start out with hydrogen gas molecules and oxygen gas molecules. In the presence of burning, these molecules break their original bonds and reform with each other, forming water. So how do you represent a chemical reaction? Representation is a model that shows what's happening in the chemical reaction. So we use chemical equations to represent these. For example, solid sodium combines with chlorine gas to make sodium chloride. And here we see a chemical equation to represent this reaction. So this tells you, this number here tells you the number of sodium molecules, or in this case atoms that you start with. We're starting with 2 sodiums. In parentheses, the S indicates that it starts out as a solid. This symbol tells you what that compound or element is combined with. And in this case, that's chlorine. In parentheses, G, telling us that chlorine is a gas. And this is a molecule that's composed of 2 atoms. So the subscript tells you how many atoms are in the molecule. The coefficient tells you how many molecules or single elements if you need that. And then you have this arrow. The arrow indicates the word yields. Yields is, you can kind of think of it like the equal sign. So this tells you, after that, the products. On this side we have the reactants, on this side we have the products. In this case, 2 sodium plus a single molecule of chlorine gas gives us 2 NaCl molecules. NaCl being the compound that is formed, and if our equation is balanced, we have 2 of them. So the chemical equation is a shorthand form for writing what reactants are used and what products are formed in a chemical reaction. Sometimes the equations can also show whether energy is either being produced or absorbed during the reaction. For example, 2H2 plus O2 yields 2H2O. So we have reactants on the left-hand side. This is what we start with. It's kind of like the starting ingredients in a recipe. Then we have the yields, or the equal sign, and the products are on the right-hand side. Another example of a chemical equation is CH4 plus 2O2. So we have 1 CH4 molecule plus 2 oxygen molecules gives you a CO2 molecule and 2 water molecules. Or finally, C6H12O6 plus 6O2 yields 6 CO2 plus 6 H2O plus energy. If we read this in words, this would be glucose plus oxygen yields carbon dioxide plus water plus energy. And this is the formula for cellular respiration, which is how all organic matter gets its form of energy. So we've talked a little bit about this already. There are certain components, certain vocabulary terms you need to know when you're talking about a chemical equation. And they're represented with these circled items here. Each component of the equation is a chemical formula. The formula tells you the substance that you're working with. In this case, we have 3 formulas in this chemical equation. The numbers that are written slightly lower and to the right-hand side of various elements in our periodic table, those are called subscripts. Think of a subscript like the subway. It goes down below. The larger numbers to the left of various components are called coefficients, just like coefficients in math. They tell you how many of each molecule you're working with. Then we have, as we've mentioned, on the left-hand side you have the reactants. The arrow is where you say yield or yields, and on the right-hand side you have the products. Sometimes you see yield signs that look like this. Any ideas as to what that means? That indicates that the chemical reaction can occur both directions. You can take the products from one side and break them back down into the reactants on the other side and vice versa. So we have various symbols that are used in chemical equations. It's going to be important that you know what each one means. A plus sign separates more than one reactant or product. An arrow pointing to either the left or the right represents the reactants, and the direction that the reaction goes represents going from reactant to product. And again, as we saw in the last slide, that could be in either direction. S in parentheses means solid. AQ means aqueous, which is something that's dissolved in water. L means liquid, and G means gas. So if we look here, we are labeling the parts of this equation. On this side we have the reactants, on this side we have the product. These larger number 2's are the coefficients, and these smaller number 2's are the subscripts. There are several types of chemical reactions that we are going to take a look at. The first one is the synthesis reaction. In this reaction, 2 or more substances combine to form one product. That's a key to remembering what a synthesis reaction is. And you may remember this from your video that dealt with the Flintstones. So the general form for synthesis is A plus B yields AB. A real reaction might be 2 magnesium plus oxygen yields 2 magnesium oxide. The next type of reaction is decomposition. This is when one reactant is broken down into 2 or more products. And the general form, this is the opposite of synthesis. So synthesis, decomposition, they go opposite directions. Decomposition would work from AB, which is one compound, yielding A plus B, 2 separate compounds or elements. For example, 2 magnesium oxide yields 2 magnesium plus oxygen, which is the reverse of what we just saw. Another example is 2KClO3 yields 2KCl plus 3O2. A third type of reaction is called combustion. This is any reaction that involves the process of burning with oxygen. One reactant is always going to be oxygen, the other is often a combination of carbon and hydrogen. The products of this type of reaction are always carbon dioxide and water vapor. For example, CH4, which I believe is methane, plus 2O2, or oxygen, yields CO2 plus 2 water, or carbon dioxide and water. Another type is a single replacement reaction. In this type of reaction, an element reacts with a compound to form a new element and a new compound. So you're forming new combinations here. The general form is A plus BC yields AC plus B. So what you can see is we have a single element and a compound. In the product side, that single element is now combined with part of the other compound, leaving a different single element. So one component of the compound gets replaced with that single element. For example, magnesium plus 2 hydrochloric acid yields magnesium chloride plus hydrogen gas. A double replacement reaction is where you start out with 2 compounds and then they react with each other to form 2 new compounds. So they basically have one component flip-flop spots. AB plus CD yields CB plus AD. So we started with A, and the A and the C flip-flop spots. So we have HCl plus NaOH yields NaCl plus HOH. And incidentally, this is also an acid-base reaction. So hydrochloric acid plus sodium hydroxide yields table salt and water. So the next question we need to consider is, what is the law of conservation of mass and how does it apply to chemical reactions? This law states what we will see right here in this video.
The law of conservation of mass states that in a chemical change, matter is neither created nor destroyed. It is only rearranged. For example, let's place 5 zinc and 5 sulfur atoms onto the two sides of a pan balance. The two sides balance because the contents of each pan are identical. Consider the reaction of zinc with sulfur atoms on one side of the balance to form zinc sulfide. 5 zinc atoms will react with 5 sulfur atoms with a tremendous release of energy to form 5 zinc sulfide molecules. The two sides still exactly balance. The total number of zinc and sulfur atoms on each side are still identical, demonstrating the law of conservation of mass.
So basically, this law is very similar to the law of conservation of energy, in that it's saying that in a chemical reaction, atoms are not created and they're not destroyed, but the products and the reactants use those atoms to rearrange into something new. So all atoms that are present in the reactants are also there in the products. The chemical equation, therefore, has to account for that. It has to show that the number of atoms on one side is equal to the number of atoms on the other side. For example, if we look at our hydrogen plus oxygen yielding water equation, on this side, so far we have 2 hydrogens and 2 oxygens. So far on this side, we're not balanced yet because we have 2 hydrogens as accounted for by the H2, but we only have 1 oxygen atom. So in this present form, the chemical equation does not represent the conservation of mass. In order to show that, you would have to add the coefficients to basically add up more atoms on one side or the other, or both, in order for things to be balanced. Here we added 2 hydrogen molecules, so now we have a total of 4, because these are each H2, so 2 times 2 is 4. And then we would also have to add the coefficient for 2 water molecules at the end. So we still have 2 oxygens, 4 hydrogens on this side, and 4 hydrogens on this side. So we have some hints for balancing equations. First, count the number of atoms. List the number of atoms of each element to see which elements are not balanced. Then, use a coefficient to add atoms to one side of the equation. Start with whichever reactant or product has the greatest number of different elements. Add a coefficient to another reactant or product. Make sure that those are in your balanced equation are the smallest whole numbers possible, so reduce if you need to. They should have no other common factor besides 1. And as we look more into this, we'll be looking at page 83. Warning: when you're balancing equations, do not mess with the insides of polyatomic ions, put a square around them, or label them as the whole polyatomic ion as though it were an element. And don't ever play with the subscripts that you find in any compound. So these little numbers here at the bottom tell you how many atoms are each, how many atoms of each you need in that one molecule. So to review the law of conservation of mass, matter is not created or destroyed. Atoms are rearranged in chemical reactions. Chemical equations represent chemical reactions, and you have to have the same number of each type of atom on the left that you do on the right. One more thing about energy in chemical reactions. It takes energy to break bonds. The more stable the bond is, the more energy you need to break it. So if we think about these two pictures here, you've got something that's very stable and is going to require a lot of energy, and then you've got something that's somewhat unstable and is not going to require a lot of energy to separate. Also, energy is given off when bonds are formed, becoming more stable. The more stable the product, the more energy is given off when it forms. There are two terms, I guess, that we use to describe the energy related to chemical reactions. You can have an exothermic reaction or an endothermic reaction. Exothermic reactions are when energy is being released. More energy is released when products form than the energy that's needed to break the bonds. For example, respiration, which we saw earlier. Or you can have an endothermic reaction. This is a chemical reaction in which energy is absorbed. More energy is required to break bonds that is released when products are formed. For example, the opposite of respiration, which is photosynthesis. You can kind of think about exothermic reactions and endothermic reactions like the chemical hand warmers and ice packs that you can, when you break them apart on the inside, they either release compounds that mix with the outside compounds that either make the ice pack seem really cold, that would be an endothermic reaction, or make the heat pack seem really warm, that would be an exothermic reaction. If you have questions, please make sure you send me an email.